In this section, we're going to discuss relativity of length. Consider a spaceship moving towards Proxima Centauri, the closest star to Earth, at nearly the speed of light. So we're a spaceship moving toward the star at nearly the speed of light. Now, Alpha Centauri is actually a star system consisting of Proxima Centauri, Alpha Centauri A, and Alpha Centauri B. So in this case, the spaceship is just moving towards the one star, Proxima Centauri. An observer on Earth measures a longer time interval for the spaceship to get to the star than the navigator measures to get to the star due to time dilation. The navigator measures the proper time, delta t p, related to the time measured on Earth, delta t, where the Lorentz factor is greater than 1. So this is a substitution that should look familiar. All we're doing here is substituting. We've seen this equation before where delta t is equal to gamma times delta tp. All I'm doing is substituting for the Lorentz factor, 1 over square root of 1 minus u squared over c squared. So the time measured on Earth is related to the time measured on the spaceship through this Lorentz factor where it is greater than 1. An observer on Earth is at rest relative to both the Earth and the star Proxima Centauri. The observer measures the distance between the Earth and Proxima Centauri as L sub p. This is the proper length between the Earth and the star. Proper length is the length measured by an observer who is at rest with respect to the two endpoints. Both the Earth observer and the spaceship's navigator agree that the spaceship's speed relative to the Earth, v, is the same. Okay, so I solved the velocity equation that we know for distance. It's velocity times time. Since v is the same, and the time is different for the Earth observer and the spaceship navigator, the distance observed by these two people must be different. The spaceship observer is measuring proper time as the measurement of time occurs on the navigation deck when the ship starts at Earth and reaches Proxima Centauri. So, proper time measured by the spaceship navigator. The Earth observer is measuring proper length. The Earth observer starts the clock on Earth and then stops it when the spaceship is at a different position, the star. All right, since the velocity is the same, we can put these two equations together. So for the Earth observer, the proper length is the speed of the spacecraft times the observed time, delta t. Now, for delta t, I'm just substituting for delta p and the Lorentz factor. Okay, so the Lorentz factor is 1 divided by root 1 minus u squared over c squared, and then multiply all of that by the proper time. Okay? Now, here's what we have to notice. The velocity times the proper time measured, we know what that is, right? That is the length measured, or the distance measured by the spaceship navigator. So I substituted for that. And now I have the proper length relative to the length measured by the spaceship navigator, or the length traveled by the spaceship navigator in terms of the proper length. So these equations are the same. One is just solved for the proper length, and the other is rearranged and solved for the length from the perspective of the spaceship navigator. The Earth observer measures the longest distance, the LP, the proper length. The spaceship navigator measures the length contraction distance, what's called the length contraction distance, or what we see here as L. So that contraction length will be less than the proper length. So it's possible that the same observer may not be measuring both proper time and proper length. In the spaceship example, the spaceship navigator measures proper time. How long does it take the spaceship to get from the Earth to the star? Measuring on the spaceship is that proper time. But that navigator is measuring a contracted length, right? Because the star is getting closer and closer as the spaceship gets closer to it. The Earth observer is measuring dilated time as the spaceship moves further and further away from the Earth at rest, but it's measuring the proper length, the distance from the Earth to the star. Dilated time is always greater than proper time, and contracted length is always less than proper length. So this Lorentz factor, this is always, the Lorentz factor is always greater than 1. The 1 over square root of 1 minus u squared over c squared is always greater than 1. So we're always going to get a delta t that is greater and a contracted length in L that is less than the proper length. So what happens to the length of a spaceship moving near the speed of light as observed by a stationary observer outside the spaceship? Got to be careful. In this case, the proper length of the spaceship is measured by a crew member on the spaceship. The stationary observer measures the contracted length. So the contracted length is the proper length times the square root of 1 minus u squared over c squared. And the contracted length would be less. So the contraction only occurs in the direction of the motion of the spaceship. So, and look at how much the contraction increases as the speed of the spaceship gets closer and closer to the speed of light. Okay, here's example 4, looking at length contraction. Particles in the SLAC National Accelerator Laboratory can travel the 300-meter beam line. So that is the length. The proper length measured of the beam is 3,000 meters. At speeds of, so point U is 0.999 c. Very near the speed of light, right? But not quite. How long is the beam line in the frame of reference of the particle? So the particle of light itself that's moving. What length is its frame of reference measuring? So that length is the proper length times the square root of 1 minus u squared over c squared. 3,000 meters times the square root of 1 minus u squared is 0.999 squared times c squared over c squared. So I can get rid of these. And then I've just got to do some calculation here. So 1 minus 0.999 squared is 0.001999, and then the square root of that is 0.00447 Then multiply that by 3,000, and we get 134.13 meters. So it should be less, right? We get a contraction of length. And because this is moving so fast, like 99.9% the speed of light, it makes sense that we get that great contraction. So think back to that previous slide where we saw that as we got closer and closer to the speed of light, the contraction was greater and greater and greater and greater. So a much less distance, a much smaller distance than the proper distance. All right, so this slide just goes over the solution. Just make sure that you have your givens properly. So the proper length and the u, the speed relative to the speed of light, and then make sure that you also calculated your length to be 134 meters.